All right, let's just dive right into this explainer. Today, we are going on a fascinating microscopic journey. We're going to track a single data packet's epic 7-stage journey across the internet using WireGuard. If you've ever found yourself wondering exactly how a modern VPN tunnel operates under the hood, step by step, you are absolutely in the right place. We're breaking down the mechanics of a WireGuard tunnel path, and we're going to follow a piece of data from the exact millisecond you click a link all the way to its final destination, and then all the way back. But first, we really have to ask, how does your private data actually survive the chaotic, totally unpredictable public internet? I mean, think of the open web as hostile territory. It's this crowded, noisy jungle filled with prying eyes, automated snoopers, and data sniffers. Whenever you send a request without any protection, your data is essentially just wandering through that jungle completely exposed, wearing a giant name tag with its home address and destination written in big bold letters. So our goal today is to see exactly how WireGuard builds this impenetrable, armored transport vehicle around that vulnerable traveler, letting it cross the jungle completely undetected. Okay, let's start right at the beginning with stage 1, starting the packet's journey. At this initial stage, things are actually remarkably mundane. You open up a browser, maybe an app, or a script fires off a request. What is absolutely crucial to understand here is that at the application layer, there is zero awareness of WireGuard. The application is completely oblivious to the fact that a VPN is even running. It simply does a normal DNS lookup and tries to connect to an IP address and a specific port. It just hands this request down to your operating system's networking stack, just like it would on any normal network. So what we have at this exact fleeting moment is highly vulnerable plain text data. It's paired with a destination IP, usually the internal or VPN-assigned IP of your application server, and a port number. It is completely 100% exposed.
But now we move into stages 2 and 3, the WireGuard armor.
This all happens on the client side in literally a matter of milliseconds. As the app sends out its vulnerable request, we hit stage 2, which is the operating system routing decision. Before that packet can even reach your physical network card, way before it touches your Wi-Fi antenna or an Ethernet cable, the OS checks its internal routing table. See, when you turned on your WireGuard client, it quietly slipped in a new rule. This rule says that any traffic destined for your target network, which is defined by your allowed IPs setting, has to be intercepted. So the operating system just silently redirects those matching packets away from your regular everyday network interface. So where is it redirecting them? Well, it sends them to the WG0 interface. Now, WG0 isn't a physical piece of hardware. It's a virtual, entirely software-based network interface running right there on your device. Its entire reason for existing is to process and encrypt traffic instead of just blindly blasting it out over your local network. When the OS redirects our vulnerable plaintext packet to WG0, we officially enter stage 3, encryption. Inside that WG0 interface, a massive transformation takes place. Your naked plaintext data goes in, and the interface applies some seriously state-of-the-art cryptography. Because it already did a handshake with the VPN server earlier, using the noise protocol and a curved 25519 key exchange, it's got a secure derived session key ready to go. It uses ChaCha20 Poly 1305 to encrypt the entire original packet, headers, payload, the whole thing. Then it takes that newly encrypted blob and wraps it up inside a brand new UDP packet. The original packet is just gone from view. What comes out is this opaque, encrypted blob, a UDP payload with a completely new outer header showing your real public IP as the source and the VPN server's real public IP as the destination. It is locked up tight. Now, fully armored in a digital steel briefcase, we enter stage 4, crossing the public internet. So as our encrypted UDP packet travels across your ISP's infrastructure and bounces around through various public internet routers, people might be watching, right? Hackers, ISPs, government censors. But what do these snoopers actually see? Well, they see your public source IP, they see the VPN server's IP, they see it's using a UDP port, which is typically 51820, and they can measure the packet's size and timing. And that is literally it. What they absolutely do not see is the content, the true internal destination, or what specific application you're trying to access. WireGuard just perfectly hides the packet's true intent behind an impenetrable wall of cryptography. To anyone looking, it's just random noise. Our packet miraculously survives the hostile jungle of the public internet and safely arrives at its destination, bringing us to stage 5, the critical trust boundary. This crucial moment is captured perfectly in our source material, which notes traffic goes from unreadable ciphertext to plain text right here. This happens at the VPN server's own WG0 interface. But it doesn't just blindly crack open the briefcase. The server acts kind of like a strict bouncer at a club. First, it checks the sender against its list of known peer public keys. Then, it verifies the packet's timestamp counter to guarantee this isn't just some hacker trying a replay attack. Only after it proves the encryption is completely valid does it actually decrypt the payload, recovering that original plaintext packet we started with. This is the moment of truth. The VPN server now knows exactly what you are requesting. The armor comes off. With the data unpacked, we move right along to the final leg of the journey, stages 6 and 7, reaching the final destination. At stage 6, the VPN server basically changes hats. It's no longer just a cryptographer, it becomes a router. Holding your freshly exposed plaintext packet, the server consults its own internal routing and forwarding rules. Usually, it applies firewall and network address translation, or NAT rules as well. It takes your request and just forwards it deep into the internal private network, pointing it straight at the application server's internal IP address. And because of that NAT translation, the application server almost always just sees this traffic as coming from a consistent VPN internal source IP. And again, blink and you'll miss it. The plain text packet leaves the VPN server, shoots across the secure internal network, and successfully arrives at the application server in milliseconds. Which brings us to stage 7, which I honestly just like to call blind trust. It's actually kind of funny when you really think about it. The application server is completely clueless about the epic, armored journey this little packet just took across the globe. It receives what looks like a totally normal, boring internal network request. It's in plain text, and it's coming from a trusted internal IP. The app server has no idea whether you were sitting at a desk right down the hall or logging in from a coffee shop on the other side of the planet. It just processes the request normally, blindly trusting that because the packet came from the VPN server, it already passed all the necessary access controls. And then, the magic happens all over again, entirely in reverse. The app server generates its response, and this data traces the exact same 7-stage path backwards. The reply goes to the VPN server, it gets immediately re-encrypted into a brand new UDP packet, it crosses the hostile internet completely safely, arrives at your device's WGO interface, gets decrypted, and is finally delivered as standard plaintext right back to your application. A full round trip around the world completely shielded in mere milliseconds. It is just a stunning feat of modern engineering. But as we wrap up this explainer, I do want to leave you with a bit of a provocative thought. Since we just established that traffic goes from unreadable ciphertext back to vulnerable plaintext right at the VPN server, who are you really trusting? I mean, WireGuard's encryption is practically bulletproof in transit, but that critical trust boundary at stage 5 means whoever owns the VPN server can absolutely see your traffic. If you're using a commercial VPN provider, you're basically just shifting your trust from your local ISP directly over to that VPN company. It is a brilliantly designed system, for sure, but it relies entirely on the integrity of the server holding the keys. Just a little something to think about the next time you connect. Thanks for joining me on this deep dive, and keep learning.